Hi everyone and welcome back to Fundamentals of Engineering with Farhad. Mechanics of Materials. We want to calculate the maximum deflection in a fixed support beam with a concentrated load of P at its center. So in this example we want to solve our problem with the moment area method, which is our solution one, and in next video we'll solve it with the combined method. Based off the name of the method, definitely we know we need the moment diagram. The moment of this such problem is comes from two parts. The first part is the moment from the concentrated load at the center, and the other one, because it's a fix, there is a MA and MB at the fixed ends, and they are identical due to the symmetry. Now let's create the moment related to P. So we do know half of the load goes by support A and the other half with support B. So R sub A is equal to R sub B, and each of them handling half of the load P over 2. And if you create the moment base of that, it just says the moment start at 0 and increase to the center. If this theta is P over 2, it just times L over 2, and that's PL over 4 EI at the maximum for moment related to concentrated load. And the other half, it just gives us a downward movement of MA, and it just moves all the way to B. And the key to solve such problem is theta A with respect to B is equal to 0. If we draw the deflected shape of this beam after loading, you can easily see this is delta maximum, which occurs here at the center, and theta A is equal to 0 because it's fixed. Theta B is equal to 0, so theta A with respect to B is also 0, and that's the key to our problem. And it just says, based off the first moment theorem, it just says theta A with respect to B equal to 0. It just says area under the moment diagram is equal to 0. So if that's the case, if we develop dissects the area in two parts, like the first part is two of these triangles, 2 times half of PL over 4EA times L over 2, which is the half of the length of the beam, plus the greenish area is two of these small rectangles, 2 times M sub A over EI times again L over 2. And if that's equal to 0, it just says M sub A is equal to negative PL over 8. And the negative, it just says it's a downward movement. So if we know our MA is PL over 8, that's identical to MA. MA is PL over 8, that's identical to MB. And now for calculation of delta maximum, we need to use the second moment area theorem, and that just says if we draw a horizontal line from the center line and calculate the tangential deviation of this vertical line from A with respect to center, that's exactly the amount of delta maximum. If you look at it here, TA with respect to C, tangential deviation of A with respect to C is exactly delta maximum. So in such case, we just and we do know that TA with respect to C is area under EI times X bar. And X bar is also dissect to two parts. So the first part is the centroid of the top part from A, and the other one is centroid of the second part from again A. Delta maximum is equal to tangential deviation of A with respect to C. If that's the case, we just need to calculate our X bar for both part, and we do know for rectangle, for triangle, that's 1/3 from the base and 2/3 from the other part. So X bar is 2/3 half of the L for triangle, and for our rectangle, that's half of L over 2. So if we know our centroid, if we do know our area, so let's say this is the area of the top part, and we just need half of them because we are moving from A to the center. That's half of PL over 4EA times L over 2 times 2/3 of L over 2 plus the this is the area part. Mhm. This is the centroid plus the bottom part, the greenish area MA over EA times L over 2 for this rectangle times half of L over 2. This is again X bar for the bottom area. So if you do the math, it just gives you MA is equal to, sorry, if you do the math, it just gives you delta maximum is equal to TA with respect to C. Take the numbers out, that's PL cubed over EI times 1 over 16 times 3 plus negative 16 times 4, 1 over a negative 1 over 16 times 4 PL cubed over EI. And if you do the math, it just gives you delta maximum is T tangential deviation of A with respect to C, and for a fixed support with a concentrated load, that's equal to PL cubed over 192 EI. So again, for such problem, we don't have any theta at A and B due to the fixed support, and delta maximum is equal to PL cubed over 192 EI. Thank you for watching. We'll solve this problem with the combined method in next video. Thank you.